Hi everyone, my name's Ace and this presentation summarises my research thesis on building an infrared horizon sensor for orbital navigation for small satellites. So in orbital navigation, it's critical for the spacecraft to have knowledge of its position and orientation in 3D space so that any payloads or equipment carried by the craft are correctly oriented to perform their intended functions. So one of the common sensors that's used for attitude determination while in orbit is something called a horizon sensor. And these sensors analyze the shape and relative angles to the horizon edge transition. And from this, we can figure out where the local vertical to the planet is. So this local vertical is referred to as the nadir vector, and it represents an imaginary line extending from the center of the orbited body to the orbiting craft. So ongoing miniaturization of technology has led to a growing demand for compact, efficient and cost-effective navigation solutions that innovate on existing research. And a key facilitator of this has been the CubeSat specification, which defines standard interface and dimensional requirements for satellite designers to adhere to. So in image-based horizon detection, this is typically done in the visible band. This is due to the commonly low resolution of the infrared sensing arrays. But there's a lot of advantages to detecting the horizon in the infrared band versus the visible band. One of these is obviously when you're in eclipse behind the Earth, there's no visible light, so it's hard to detect the edges, and also false edge detections in cloud cover and other geographic features. Whereas the infrared band, the atmosphere creates an opaque and uniform appearance for the sensor, which makes it easy to detect the horizon edge. So this research adapts recent breakthroughs in subpixel edge localization from visible band cameras and adapts this to the infrared band to improve the edge detection resolution of these sensors. So this will be demonstrated by building an infrared horizon sensor and a simulated orbital view test stand to assess its utility. So the reason for building a physical prototype gives better contextualization around the integrated system, particularly in the context of the space environment and other real-world considerations required in the design and construction of a working model. So this work ultimately seeks to bridge theoretical research and practical application. So here we see an illustration of the edge detection accuracy that's common on these typically low-resolution infrared sensors. So this research will be applying a subpixel edge localization technique, which is from new research in the visible band camera space, specifically the Zernike polynomials. So these Zernike polynomials, they describe certain optical aberrations and were originally introduced in the context of improving telescope lenses, but their unique mathematical properties have since found applications in various other fields. So this research will be adapting this novel approach from the visible band camera space to the infrared sensors to improve their edge detection performance. So there's two key concepts to understand that will give us a better intuition about how the sensor perceives the horizon edge. The first is that the thermal sensor is represented using the pinhole camera model with no lens. So this allows us to place a world image plane in object space, and it gives us contextualization about how points in 3D space are mapped to the 2D array of the sensor. Now the second concept is that the craft's view of the Earth is restricted to the area bound by its visible horizon. So this imaginary view cone essentially represents tangent rays from the horizon edge transition. The cone's shape is dependent on orbit altitude. The apex of the cone sits at the spacecraft, and the surface of the cone is tangent to the planet sphere. So combining both these concepts together and considering the definition of a conic section, which is the shape formed by the intersection of a plane and a cone, it may become clear that the pinhole camera's world image plane in object space forms a Euclidean plane that intersects the horizon view cone at some angle. So this implies that the circular visible horizon on the 3D planet sphere projects a conic section to the 2D sensor array. So the shape of this conic is dependent on orbit altitude, the field of view of the sensor, and the orientation of the sensor relative to the cone's central axis, which in this case is the nadir vector. By mounting the horizon sensor to a precisely controlled pitch and roll gimbal while it views the simulated orbital scene at various orientations, its navigation outputs can then be evaluated against the physical orientation of the sensor. So the main considerations with the design of the test stand was ensuring that the temperature delta between the two plates approximate that as seen from orbit, and that the accurate conic projected shape was represented on the front face of the test stand. So to guide the overall project, a requirements verification matrix was established with explicitly defined success criteria for each of the requirements. This was written in the context of designing for a space-bound craft, specifically a CubeSat. So each requirement was chosen to validate the overall project outcomes. One example is the precision of the pitch and roll gimbal, which was used to constrain the physical roll angles used in subsequent calculations. The infrared sensor selected for the prototype is a thermopile matrix. It has 32 by 24 pixel resolution and a 55 by 35 degree field of view. Other considerations related to the design of the prototype relate to component selection, thermal, electrical and environmental considerations, specifically in the context of the space environment, and PCB design best practices. So CubeSats typically have a limited supply of resources available, so a low power control unit was targeted, and for this reason a ARM-based microcontroller from STM with a large allocation of memory to process the images was selected. So here we can see on the right the assembled horizon sensor prototype, and on the left is the pitch roll gimbal that the horizon sensor is mounted to while it views the simulated scene. So for the prototype's firmware, unfortunately as of writing there's no widespread support for common feature-rich computer vision libraries such as OpenCV on ARM-based microcontroller platforms. And because memory management was a key concern, it was decided that a custom C++ computer vision library could be built using low-level linear algebra libraries. So each image is represented using a matrix, and this allows an implementation of image convolutions and other commonly known image processing and edge detection algorithms. So for the attitude estimation, this is calculated using the geometric properties of the conic section. So we first have the z-axis rotation, which relates to the rotation of the conic within the sensor's image frame, and the x-axis rotation, which relates to the angle of the conic cutting plane relative to the cone's central axis, or the nadir vector. So this is based on the shape of the actual conic in the image frame itself. So overall, all the project requirements were deemed to be satisfied. Here we can see an example of the image pre-processing and coarse edge detection. So we have the initial image up here. This is after the application of a Gaussian blur. This is the edge candidate mask from this image. So we can see the white lines, white dots here represent the strong edge candidates and the grey represents the weak edge candidates. And then this is the identified edge sequence in the image. Here we see an example of the simulated orbital view. So we can see this is the verification against a calibrated thermal camera. Here we see the results of the subpixel edge localization. So this is the image frame from the prototype as it looks at the simulated orbital view. So the blue line here represents the coarse pixel level edge detected, and then the red line represents the subpixel localized edge. Here we see the results of the conic fitting while looking at the test stand from various roll angles. So the yellow bounds at the top and the bottom of this graph represent the extents of the success criteria, and this is representing an approximate 700 km LEO orbit altitude. So it was evident through testing that the subpixel edge localization allowed a much tighter inlier tolerance to be stipulated on the conic model fitting, and it was deemed to be a key contributor to the accuracy that was able to be achieved. So to give us better context about how these 3D attitude estimations will be displayed in the slides, we'll run through a quick example about how the prototype processes images and then performs an attitude estimation. So on the left-hand side here, we see an image from the prototype while it's looking at the simulated orbital scene. So first the prototype will identify the coarse edge and then perform a subpixel edge adjustment. So from those subpixel edge coordinates, we then fit 5 conic models. And then from these conic models, the geometric properties of the conic, we can calculate the rotation of the conic within the frame, as well as the plane, the angle of the plane relative to the nadir vector that was used to create the shape. So if we imagine we're looking sort of at the image frame here, this would be essentially down the bore of the detector. We add our image frame over this. We can imagine that our nadir vector might be sort of pointing up this way somewhere towards the center of the orbited body. So the way this is displayed, we've got our z-axis here in the middle would be down the bore of the detector. Our green vector here represents the actual location of the nadir vector, and that's based on the physical rotation of the pitch and roll gimbal. And then our orange vector here represents the average of those 5 conic models that were fit. This is the attitude estimation from the prototype. So we can see this has just been rotated around, so our negative z axis here would be essentially down the bore of the detector, so we're looking from the test stand sort of towards the prototype horizon sensor, and it's displayed this way just so we can get a better idea of where those vectors are pointing from this side of the unit circle. Here we see the attitude estimations from the prototype horizon sensor as it views the orbital view test stand at various roll angles. And overall, it was able to achieve a attitude determination of ±5 degrees of the simulated nadir vector. One of the main contributors to why this tolerance wasn't able to be smaller is related to the rotation of the conic in the image frame. So we can see if we look at the unit sphere over here, these obviously 2 vectors. We've got the green is representing the actual location of the nadir vector, and the orange is the attitude estimation from the prototype. we can see that the difference between these two vectors is mainly related to the angle around the z-axis here, and this is related to the rotation of the conic in the frame, whereas our angle from the xy plane out to the two vectors is relatively consistent between all the angles tested. This is also displayed over here. We can see these are the example of two models that were well fit to the edge coordinates. We can see these blue dots here represent the subpixel adjusted edge, and then these are the two models that will fit. We can see they're both well fit to the points, but they're at slightly different roll angles, which is causing this inaccuracy in the rotation around the z-axis here. So it was proposed that a wider field of view sensor may be able to better fit the models. If we have sort of a wider information about the horizon edge arc, we'll be able to get some more refinement around the actual rotation in the frame. Obviously the sensor is only 32 by 24 pixels as well, so it's proposed that a higher resolution sensor would also be able to aid in sort of providing the subpixel adjusted edge more refinement so that those small differences in the rotation can be fit to the model correctly. The second point, which requires some further investigation, is related to the detector response rate. So the thermopole detectors are thermal detectors as opposed to photonic detectors, and these inherently have a slightly slower response to thermal change when the sensor is rapidly moved or the scene changes. And this appears as a ghosting artifact in the image, which obviously could be problematic for when the craft is experiencing high rates of rotation. It was proposed that a high quality sensor may have better response characteristics than the one that was selected for the prototype. So ultimately, this study contributes to the field of infrared horizon detection research, hopefully supporting a new generation of navigation solutions that are tailored to the constraints and demands of small satellite platforms. Thank you so much for your time and listening to my project thesis.